But we know that, but from previous discussion, we know that symmetry operator must be Hermitian. Or, sorry, U is unitary from previous argument. Yeah. So this implies that since U is unitary, or rather U transpose equal to 1, actually U, so U transpose U equal to 1, then this implies that EF transpose EF equal to 1, or rather this is F minus F transpose equal to 1. So the only way for this to be equal to 1, is for F equal to, this implies that F equal to F transpose. So F is we also know that from previous argument also, I don't want to rewrite this. We all know that if UH is 0, this is from previous argument, symmetry operator must be commute with the Hamiltonian. This also implies that actually the generator also will be so this in commutative form is written like this, but in the language of physics, this say that U is symmetry of the Hamiltonian. So this is how we say it. And here, generator F is a conserved observable. So in this language, I will rewrite that physical symmetry and what is conserved. Okay, here. So I will transform this table here to something that looks like this. So so that it become more transparent to you. For example, you have a symmetry here on the. So that's why symmetry is very important, because it show you what are the conserved quantity. In fact, later there is a concept of symmetry breaking, and out of that symmetry breaking, what happened or what is occurring? Okay, so we will see later that this idea of symmetry breaking later will show you the existence of boson, the Higgs boson. Why? Because why different particle has different mass, for example, and that And there is a hierarchy of this mesh. Even quark from the up down become heavier, strange charm, and even heavier top and bottom. And lepton same. Electron very light, muon heavier, tau heaviest. So why this hierarchy? So actually explained by symmetry breaking mechanism. The Higgs symmetry breaking mechanism whereby the Higgs boson ni interact with all these particle and give the mass hierarchy. Okay, so itu cerita tu di ujung lecture ni lah, sebab tak boleh tiba-tiba melompat ke situ. Okay, so for example, if you have I have derived this in last lecture that we have a space translation. But in that case, in that class, I only give you in the x direction, but it can be y and z. So this concept the linear momentum. So we don't have to go one by one. I just say, and then remember rotation. Again, this could be in the x-axis, y-axis, or z-axis. So the angular momentum in that direction give you the angular momentum. And then time translation give you the or time symmetry give you the energy conservation. Okay. And then rotation in isospace, which we had not learned yet, but never mind, is concept of isospin. So this idea of isospin will be important in nuclear physics. There are also some unknown symmetry here, 3 of them. And if you can unravel this mystery, you can get Nobel Prize. So this is a Nobel Prize question mark. Bukan murah punya question mark ni, bukan bodoh-bodoh punya question mark. Di sini you have the baryon of lepton level or lepton number. Later you will see that this idea of lepton number purely come from experiment. There is no theoretical basis why lepton number is conserved. Itu maksud question mark di sini. And then baryon number, quark quantum number. This is also, people find that charmness, strangeness, macam-macam, topness, bottomness tu, a quantum number is conserved. Of course later it is slightly violated. That's why we have the CKM metric. Dalam up dan down tu ada sedikit charm. Dalam charm ada sedikit bottomness contohnya. Mengapa? Itu sesuatu yang masih question mark di sini. Maknanya CKM metric walaupun memberikan probability of mixture tu, tapi why it mix in the first place? And what is the mechanism of the mixture? Macam tu. Maknanya kek ni ada rasa ada rasa manis dan masam sedikit. Tetapi apa yang menyebabkan dia masam atau manis? Dan bagaimana proses menjadikan dia masam dan manis? Contoh. Itu yang fizik cuba meneroka dan memahami. Dalam arti lain, mengapa dan bagaimana Tuhan buat begitu? So itu dah mula metafizik lah. So now, then you have the baryon number. So last time I told you about baryon number. So there is no strong, and then you have the no strong basis, theoretical basis, and then you have the global SU3 gauge invariant. This conserves the color charge. Global SU2 weak charge. What is weak charge? W plus, W minus. Nanti kita akan urai. Global U1 gauge invariant. Ini adalah electric charge. It's conserved. And then you have the local U1 gauge invariant. This is the EM force. Local SU2. So this is the weak force. And local SU3, color force. So those now let me, before we take a break for 5 to 10 minutes, let me just high energy physics or particle physics will definitely